Hi Anatomy students, welcome to lecture 2. Today we're going to talk about a little bit of chemistry, which is never anyone's favorite subject in this class, but I promise you'll get through it. My personal goal for this lecture is to ignore my cat for one, and second, not touch my microphone. So let's see how long it takes me to not achieve that goal, but we'll see. So please get your notes ready and let's talk about chemistry. All right. So in order to really understand a lot of how our physiology works, we have to really start to look at how the chemistry of our body works, just some very, very basic chemistry. As you go up the levels of anatomy and physiology, and if you're planning on going to medical school, you will learn so much more about this, but we're just going to get a little bit of an introduction. Some of these things you might already know if you've taken a recent biology class or a chemistry class. Some things may be new and exciting if you haven't taken a science class in a long time. Either way, we're going to try and keep things nice and easy to understand for everybody. So let's talk about it. Remember, there's only two things in the universe. There's matter and there's energy. There's different flavors of matter and energy, but you are either matter or you are energy, usually some combination thereof. So then we can get a little bit smaller and talk about, remember we talked about this last time, how small is small. So you can go into, I'll make this link active in the lecture notes. So you can go in and see, you can play with that sliding scale and see just how small things get. We're going to talk about things in this lecture on the scale of the atom. So we like to define the atom as being the smallest indivisible unit of matter. We actually can break up the atom though, and so that's not technically a real definition anymore, but it's good enough for our purposes, okay? So atom is it's really the smallest, most definable piece of usable matter. Even that's not, just go with it being the smallest, a very small piece of matter. That's not something you'll be tested on the test because its definition isn't completely accurate anymore. We just don't have a better definition. Okay, so atoms are made of three different things. They're made of protons, neutrons, and electrons in different ratios. The proton is the positive part of an atom, and it's found in the nucleus. Okay, and it's what defines which atom you're looking at. If you have two protons, you're looking at helium. If you have one proton, you're looking at hydrogen. That's it. You can't define the atom any other way than by, well, you can, but the how you name an atom is given by the number of protons it has. Once you change it, you've changed the element. You now have something different, okay? Neutrons are also in the nucleus, and they are neutral. So you can change the number of neutrons in an atom, but, oh, by the way, I keep switching up atom and element. So an atom is just kind of this generic term for something with protons, neutrons, and electrons. An element is a specific kind of atom, okay? Okay, so in the nucleus of the atom, you also have neutrons. You might have neutrons. You usually have neutrons. So neutrons, we don't know why they hang out in the nucleus of the atom. We do know if you take them away, you get a nuclear explosion. So something important's happening there. You can change the number of isotopes in something, or a number of neutrons in an atom, and you suddenly are dealing with an isotope. So you may have heard of something called carbon dating, or isotope radiation, other kinds of things, where you are creating an unstable version of the atom where it will break down faster than the other kinds of that atom, the other versions of that isotope, and then you can trace where an atom goes. So isotope radiation, that kind of thing, is used in medicine a lot. If you're going into that, you'll do more about it. That's all we're going to say about neutrons. Electrons are where chemistry happens. So electrons hang out in these orbitals around the nucleus. They are the negative parts of the atom, and they are attracted to the protons. Now, if you are thinking about it, protons are positive, I guess they're the yellow ones, then how come two positive things are stuck together? We don't know. Chemistry's trying to figure it out. Good job, guys, because I don't know. But we do know, again, like with the neutrons, if you split an atom so that the protons move apart from each other, you get a nuclear explosion. And so the fact that they are stuck together, even though they don't want to be, and when you take them apart, you have an explosion, means there must be some really strong force holding them together. Do we care about that for anatomy? Not at all. If you are losing protons within your atoms in your body, you're probably, well, I was going to say you're probably dying, but actually this happens. You may have heard that, Whoa, bananas. Bananas are partially radioactive, so is a lot of ceramic. They have isotopes in them that activate a Geiger counter, or can be picked up by a Geiger counter. But do they explode and kill us? No, it's just a natural part of nature. Okay, moving on. Why do we care about those electrons? They're going to be where chemistry happens, and they're going to be a big part of how chemicals react with each other. Okay. So, what does that mean? Okay, so here is Big Daddy Dmitry Mendeleev, who is the father of the periodic table. Okay, he has not only a super impressive beard, but he is the guy who organized the periodic table. It didn't exactly look like this, but he got so close without actually using a microscope or anything that we still give him a lot of credit for it. Now, we don't care about this, but if these two rows should be on here, but that would make the periodic table way too long to fit on a page, so they are not there. Also, this periodic table is actually out of date because all of these have been identified. So we'll just leave it at that. But what you'll notice is if you were to zoom in on these, let's say I zoom in on nickel. Well, there's these numbers involved. What's happening? But you'll notice these numbers go in order. These numbers have a decimal point. What? So this is our atomic number. The top one with no decimal is our atomic number. That tells you how many protons it has. Remember, protons define your element. So if you're looking at something that has 27 protons, you're looking at cobalt. On the other hand, this is the atomic mass, or how much matter is present. So that's your protons plus your neutrons. The easiest way to figure out how many neutrons you have is to round this number to the nearest whole number, so 59, and subtract this number. Okay, so you'd have 59 minus 27. That's going to be your number of neutrons. Again, not crazy important for this class, so let's move on. It is important in that you should know it just because it's basic chemistry, but it's not fun anatomy stuff. So here's what I was just saying. The atomic number here is the one that never has a decimal point. That's how many protons you have. While the atomic mass number is the one that always has a decimal point, and it tells you how many protons plus neutrons you have. Okay. So, if we were to look at this guy and we were to say, oh, it has a neutral charge, what does that mean? So neutral charge means that there's no positive or negative charge on this atom, which means if you have a bunch of protons and they're positive, they must be canceled out by the electrons that are around it. So we don't even have to look at the number of protons, and we can know that, okay, so if it's neutral, we must have the same number of protons and electrons. We know the electrons are around the atom. So I'm going to count. I've got 1, 2, I've got 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons, which means I must have 11 protons, which means this must be, oh, let's go back to my periodic table. 11 is sodium. So number 11, sodium, that must be our answer. That must be what that element is, what this is. How fun, you guys. Yeah? No? I love it, but that's why I teach. Okay, goodbye. Let's keep talking. Okay, so let's... all I want you to know about the orbitals on an atom are that they are where the electrons live being not actually accurate, but that's where the electrons are most likely to be found. And it's that whatever the outermost ring is, that's where your active electrons are. Now, there are some other ones that are important in some other species and sometimes in some medicine. You have electrons that move from outer shells down into inner shells, and those are they're more stable when they're closer to the nucleus. The further away, the more likely they are to run away or be stolen away. And so they have higher energy because they can kind of escape the trap that is the nucleus's charge. And so there are cases where sometimes this outermost electron will drop down to a more stable level, and when it does, it emits light. And so that's how you get things like fireflies, or if you've been in the oceans in the last couple months, you've seen this bioluminescent sand and waves, and that's a bunch of algae that are producing this kind of reaction, and it's very exciting. Do humans do it? We do, in a very, very low level that we actually cannot see, but there are times when our cells are dividing where we do produce light. Interesting. But most of the time, all we care about in chemistry is the outermost shell of electrons, because that's the one that's going to be interacting with other things. Okay, so if we look at a very overly simplified periodic table, One way to think about how many electrons do I have to do stuff with is to think about what's called the rule of 8, or the octet rule. Okay, so octet being 8. Every atom wants to have 8 electrons in its outer shell. It's just a rule of chemistry, of physics. Why? We don't know. We just go with it. Okay, where the outermost shell wants to have a full octet, except for hydrogen and helium, because they don't have a total of 8 electrons. They want to have 2 electrons. That is the goal, is to have 2 electrons. Okay, so you either want 2 or 8 electrons. If you only have one shell, you want 2 electrons. If you have more than one shell, you want 8 electrons. Okay. Oh, I touched my mic. Oh, if you were betting, you win. And so how do we know how stable an atom is, or how likely it is to react with something? The further it is away from its goal, the more active it is. Okay. So the most active electrons, or the most active atoms, are the ones that only have 1 electron in their outermost shell, or the ones that have 7 electrons in their outermost shell, because they're so close. In these guys, I could either gain 7 electrons to get that full outer shell, or I could just lose 1 and drop down to that happy 2 level. Okay, same thing here. I've got 2 electrons, 8 electrons, 1 electron. I can either go and take 7 electrons from somewhere, or I can just give up this 1 and suddenly I'm stable but a little bit smaller. Okay, so the electrons that are, or any time an atom has 1 electron or 7 electrons, or as it's approaching those, it's going to be the most reactive. Okay, and by reactive I mean stuff happens. Okay, so this is where students are doing different chemical reactions. This is actually a reaction using a metal, probably sodium actually, where they just put it in water, and suddenly it's so reactive to just losing that 1 electron, oh my god, that it literally catches on fire. Okay, so if you look up a video, if you look up the chemical, if you look up the alkali earth metal chemical series, you'll be able to, and I'll make a note to put that in the alkali earth. I'll put that in the in the module, so you can click on it if you like. You'll see that as you go down the periodic table, things get really, really reactive. As you go down in that same idea of, in all of these are going to have the same kind of crazy reactivity. As you move this way, as you get to 4, where carbon is, well, you could either give up 4 or you could gain 4 to get to 8. So you could do either. So carbon's pretty stable. It makes its bonds and then it just chills. Well, wait, what's the most common element in our body? It's carbon. Oh, whenever we go and we look for life in other parts of the universe, we say we're looking for carbon-based life, because it turns out carbon is a very, very stable molecule. Okay, or it makes stable molecules because it's not likely to suddenly give up anything or steal electrons like the ones in this row or this row, which is technically, let's go to a real periodic table. Boop. This row 1 and row 17, are the most reactive chemicals on the periodic table. They're so hyper to just get rid of or steal 1 final electron. They're so crazy. However, anything in row 14 is pretty chill. It does whatever. It's going to react, but it's not going to react crazy. It's going to make nice stable bonds. However, anything in row 18, they already have their happy octet. They don't need to do anything. They're called the noble gases, or the inert gases. They don't do anything. To be inert is to do nothing. So if you're like me during this quarantine, a lot of what I've been doing, I've been very inert. It's not great, but it's getting better. Okay. So why are we talking about chemistry when this is an anatomy class? Well, guess what? Our body is full of chemistry. So while the earth is mostly oxygen and silicon, our bodies, so we evolved on earth, we should be pretty similar to what's on earth to be efficient, right? Well, technically our bodies are 65% oxygen and 18% carbon. But where's carbon here? It's not even one of the major components of the earth. So that's pretty insane. But we make it work, because that's just how life evolved on our planet. Okay, fantastic. So obviously carbon, oxygen, and hydrogen are the big 3 main elements in our body. But what else is there? You can remember using this handy little guide that I like called CHNOPS. So CHNOPS being carbon, a hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So these are the 6 elements that are most common in our body. We're going to talk about different kinds of biomolecules in the next lecture, where you'll see a combination of C, H, and O gives us lipids. A combination of C, H, O and I think it's N. Yeah, CHON is going to give you your proteins. And then a combination of everything but sulfur is going to give you something else. And then the last thing is going to be our nucleic acids. It's going to be great, guys. Everything's going to be fine. You will notice there are other things, though. We're not just made of chanops, okay? Then we also have trace elements of things like calcium and magnesium and chlorine. So a trace element means that it's there. It's just not as, prevalent as everything else. Okay. So, remembering that chemistry is all about those electrons, we're going to talk about some bonding. Now, I'm going to tell you now, people hate this part, but it's going to be fine. Basically, we're trying to figure out how do you build a person if you're just starting with atoms, okay? And it's all about how those electrons interact with each other. So remember I said if you have only one electron in your outermost shell, or if you have 7 electrons in your outermost shell, you are just hungry to get rid. I just want to be stable. I'm so close. So if an element like sodium, which only has 1 electron, comes close to an element like chlorine, which has 7, you better believe they're going to react. And what happens is sodium gives up its 1 electron, so it goes down to a nice stable 8. See how it loses that outermost shell? And chlorine gets to steal that electron and get a nice stable 8 also. What? But now that means that now sodium, which was balanced, it had 11 protons and 11 electrons. Now it has 11 protons, but 10 electrons, which means it has 1 more positive charge. And so now it's positively charged. Okay. Chlorine, on the other hand, let's see. Okay, here's why you should never bother memorizing the periodic table, because you will always have access to it. So chlorine is number 17, which means that chlorine has 17 electrons, 17 protons when it's stable. 17. If I just have 1 more, I'll have stable 8 on the outside. Oh, hey, thanks, sodium. I'm going to take that. Now I'm stable. But now I have 1 more electron than I do proteins. I have 18 electrons and only 17 proteins. Now I have a negative charge. So why is that important? This is very important because that's how things will end up associating with each other. So if you put salt in water, so salt like sodium chloride, if you put it in water, it breaks down into its component parts. It's in component ions. So an ion is any atom with a charge, okay? So a charged atom is an ion. And these are also called electrolytes because it turns out this positive-negative association can conduct electricity. Okay, so you've definitely heard of electrolytes if you've ever seen a commercial for Gatorade or Powerade or whatever aid that's out there right now. They always talk about electrolytes, and you actually do need electrolytes because when you sweat, you lose those electrolytes. So what does that mean? Well, it means you're losing charged particles, and we're going to talk about how these charged particles are incredibly important in neurons. So the way that we think and the way that our muscles move all happens through electricity. And so, in fact, when someone gets shocked, if you've ever been electrocuted, when you touch like an outlet or something, one time in graduate school, I was reaching behind a bookshelf to get a plug, and I didn't realize that the plug was sticking out a little bit. It was in the outlet, but it was sticking out a little bit. And so I touched my finger to the exposed metal of the plug that was in the outlet, and I jolted and I shot backwards. When that happens, it's not that the electricity is shooting you backwards. It's that the electricity causes all of your neurons in your body to clench. And then that shoots you backwards. The fact that your muscles are clenching and like doing their thing really suddenly is what causes you to move during an electrocution. So, which actually should beg the question of like, what are humans actually capable of? Because that's crazy, right? Moving on. We'll get back to that later. The point is that these charged particles called ions happen when one atom steals or gives up an electron. Okay? Fabulous. Now, when that happens and they associate with each other, you get an ionic bond. These are the strongest kind of bonds, okay? Because it's not like chlorine's going to be like, oh yeah, I'll give up an electron now. No, it's going to stay charged, and then it's going to be attracted to that positive charge, and that's going to be great. Okay? Do I want you to know about this? I guess we'll run through it really quickly. So no, I don't care about this. Let's move on. We'll talk about it really quickly. So sodium chloride, so sodium and chlorine, that is table salt. H2O is water. If you were to put these two things together, remember when you put salt into water, it breaks up into sodium. So it's going to break up into Okay, it's not going to do it for me. Okay, thanks. You end up getting sodium with a plus charge. Oh, this is a disaster. There we go. Because now it's a charged ion plus chlorine with a negative charge plus just some water. Okay. You also, that water could dissociate and you could end up with, oh, well, if water breaks down, what do you get? You have a positively charged sodium. You end up getting part of water goes over there and part of water goes over here. What does that kind of look like? Well, this is hydrochloric acid, which is an acid. And actually, this is sodium hydroxide, which is a base. Huh, interesting. We're going to come back to that. Very important fact in a minute when we talk about pH. But let's keep going with our bonds, okay? What bonds are made or broken? So this sodium chloride ionic bond is broken. It's dissociated by water. And then the water goes in bonds. Don't worry too much about that. I'm not as concerned about it. Let's go on. Let's talk about, so ionic bonding is when electrons are stolen by two differently charged particles, okay? And it always is going to happen with something on the left side of the periodic table and the right side of the periodic table. Basically anything, usually you see this nice little stair step effect here. You can really just say anything from 13 on is going to be attracted to something from 1 to 13. And that if you have something from this side and something from this side, that's an ionic bond, okay? And it's always going to have a charge involved. It breaks down in water. It conducts electricity. Very important. The next kind of bonding is covalent bonding. And covalent bonding is when atoms share, okay? It seems so much more nice. Thank you for sharing. We all got to that part in kindergarten. We're sharing. So these are strong. This is your oils, your fats, that kind of thing. These are things that are not going to break down in water. In fact, water can't really affect them, except that water is them. Water's weird. Water's a weirdo. We're going to talk all about it. And these are the things that hold your really big molecules together. Your DNA, your proteins, your starches, etc. Those things are covalently bonded macromolecules. And the way that you can tell that you have a macromolecule is you have two things from this side of the table stuck together, or more. You can have more, but it's always going to be overwhelmingly carbon, especially in this kind of class, an anatomy class. It's going to have carbon, it's going to have oxygen, it's going to have sulfur and phosphorus maybe, it might have some nitrogen, but these are all bonding together. You might have, there's always hydrogen in everything. Hydrogen is just like the glitter of the chemistry universe. If once it's there, it's everywhere and it's never going away. And so hydrogen could bond to anything, whatever. But usually your covalent bonding is going to be happening in this region, the periodic table. Okay. Will you be given a periodic table? Absolutely. I don't care about this. We're not going to worry about this scale of electronegativity. It's very intense chemistry. I don't care. Let's instead look at this idea of chemicals at a party. So this is a beautiful video that was made, and it's a really good example of how reactions occur. And I'm going to talk a little bit over it, but you should watch it on your own because it is fabulous. Let's go. Oh, you can't hear it. That's fine. Okay, so the idea is these chemicals are all at a party. If you have hydrochloric acid and zinc, oh no, zinc can actually replace the hydrogen because hydrogen's a big old chump. It gets replaced by everything. No, it's not a chump. It's very low. Okay, look, here's neon. Neon is an inert gas. Oh, so it's not going to react with hydrogen. But hydrogen sees carbon, and carbon wants to make 4 bonds. And hydrogen, remember, will bond to anything. Oh, so there's one hydrogen bonding with carbon. There's another hydrogen bonding with carbon. There's a third. Oh, there's 4. 4 hydrogens bonding with carbon. Now, let me tell you, when I taught this in Texas 10 years ago, everyone freaked out about this. But hello, we're more mature. They're just chemicals. Again, your noble gases do not bond. Sometimes you get this covalent bonding of oxygen, which it turns out hydrogen can break up really easily. Oh, you go, hydrogen, you get it. Sodium and chloride, remember we just talked about those, they're ions. They are what are called electrolytes. They can be separated by electricity. Rude. Rude. All right, potassium, water. So potassium has 1 electron in its outer shell, which means it is very reactive, especially in the presence of water. It's just going to take it down. Oh no, it's so explosive. So normally in a chemical reaction, if we say something's explosive, it literally explodes. But this is a pretty good example of how reactive chemicals are. So I'll provide a link for this in the module because it's a very adorable video and it's just fun. And it kind of breaks up this chemistry lecture. Okay. Do I care about this? Okay, so we've talked about covalent bonds. We've talked about ionic bonds. What's a polar covalent bond? So a polar covalent bond is where these two things kind of come together. So we didn't talk about it in ionic bonds because it's kind of one of these things that if you've done chemistry, it's just assumed. And so what I'm talking about is that ionic bonds are polar. That means they have a pole. They have two poles. So like our planet is polar. It has a north pole and a south pole, which are actually have to do with magnetics. In the case of atoms or molecules, you can have polar molecules, which means it has a positive side and a negative side. So ionic molecules always have positive and negative sides. Covalent molecules, if they have a positive and negative side, it's because of something weird happening, and usually it's because of oxygen. Okay, so this is water, and water is the classic example of a polar molecule. And so what that means is you have a positive and a negative region of this covalent bond, which means it can react with all of this. So friggin' water, and usually it doesn't react with the covalent bonds so much, it just kind of chills with it, it hangs out with it, but it can react with ionic bonds, and this becomes very important. Okay, so these polar covalent bonds, they should be sharing, but they're not really sharing equally. And you get, again, a positive and a negative side. They're sort of positive, sort of negative. Usually this happens if you have a lot of nitrogen or oxygen. Okay, this makes these biologically strong. Don't know what I mean by that. Okay, cool. What that means though is that water can then go in and break up ionic compounds, which we know it does, and yet still retain its own structure. Okay, interesting. Now let's talk very briefly about hydrogen bonds. So water not only can break up other bonds, it can bond with itself, which is something pretty interesting. It's something not a lot of molecules can do. So because usually when you have like lipids, and this is my quarantine bang situation, when you have a bunch of non-polar organic molecules together, a bunch of non-polar covalent bonds together, they sort of just hang out. Okay, like oils, they don't really bond to each other. That's why they're so slippery. They're not bonded together. Okay, and then we have a hydrogen and water. We have water, and it bonds to other things and itself, which is a very unique property of water. Okay, so it's doing this because of that polarity, but it's also doing this because of these hydrogen bonds. So hydrogen bonds are the weakest of the bonds, and thank goodness, because what that means is it sucks when you're dealing with like this surface tension of water, when you have a bunch of hydrogen bonds sticking those surface molecules together really hard or really strongly, and then you belly flop on it and it hurts a lot before those bonds break. But it's really good when you're trying to do stuff like open up DNA like a zipper. If those bonds were any stronger, we would not be able to open up DNA. We would not be able to live. Okay, same thing with when you're trying to break down molecules in your food. If we didn't have hydrogen bonds, some of those molecules would never be released for us to eat. So thank you, hydrogen bonding, for making it easy for us to break up stuff. Okay, let's move on. Okay, so again, the hydrogen molecules, hydrogen bonding don't make new molecules. What they do is they instead stick things together. Okay, so this makes something. Okay, this has to do with if a molecule is hydrophobic or hydrophilic. So you might recognize the word phobia from this phobic or philia, if you're looking at that. So hydrophobic means it's scared of water. That means it's not charged and it cannot be bonded with hydrogen bonds. If it's hydrophilic, it can be bonded or broken down with water, and it can mix with water and reactions can happen. So the quintessential example being oil and water. So oil will not interact with water. It will hang out with it. But once you let it separate, oil will be oil and water will be water. On the other hand, so oil is hydrophobic. It doesn't want to hang out. It wants to bond with its own self, and it's just kind of classist that way. No, it's just the chemical reaction going on there. In the cell, it's very important because then your lipids hang out together. Your cell membranes stay together. The only reason your cell membranes stay together is because of that hydrophobic interaction. When I think about that, it blows my mind. It makes me a little nervous about biology. So why are these hydrogen bonds so important? It allows for solubility. So it allows for things to break down in the body, which is good. We need that. Okay. When you eat a vitamin, it gets absorbed, breaks down in your guts and it gets absorbed into your blood. We need it to stay broken down until it gets to where it's going. If it doesn't, it'll glom onto stuff in the bloodstream, and that's super bad. You'll get these big chunks of vitamins in your bloodstream, which we do not need. It also lends some stability to molecules like DNA. So most of the time, DNA is all wrapped up, doing its chilling thing. But if you need to open certain parts of the DNA to actually activate a gene, well, those H bonds can unzip very easily. And so independently, one hydrogen bond does nothing. But like with Velcro or a zipper, when you have a whole lot of them together, it's really strong. Okay, so thankfully, we can disrupt those hydrogen bonds very specifically so we can get in and do specific actions. All right, another important thing about hydrogen bonds is the presence of hydrogen determines how acidic something is. So a few minutes ago, I talked about how when you break down, when salt is broken down in water, you can kind of break up water also into H and OH, and then H is positive. That's just called it could be called the it could be the hydronium ion. Don't worry too much about it. And the OH exists as OH minus, which you'll see in a couple minutes, and that is the hydroxide ion, which determines if something is basic, not like Uggs and a latte basic, but like basic as in the opposite of acidic. And depending on how many OHs or Hs are present, that's how acidic or basic your solution is, okay? So your very, very acidic things actually have a pH of 0 to 1. So stomach acid is on the scale of 1 to 2. Very concentrated hydrochloric or hydrofluoric acid is on the scale of 0. Why? That's so weird. I know. Just roll with it. So here's the thing. So neutral is 7. Pure, beautiful, nothing in it water has a neutral pH of 7. If you're drinking a bottle of water right now, from whatever, if you look at the ingredients, it's not just that, because our tongues can't taste that because it's so neutral. So usually bottled water adds a little bit of alkaline something to make it a little bit basic. That's mineral water. Okay, so if you're eating mineral water, basically they put some baking soda in your water to make it a little bit more basic so you can taste it. So if you've ever been like, I think these two waters taste different, they do. Depends on what's in it. Okay, so this is very important, this scale, because on this very extreme side of the acids and the very extreme side of the bases, these will break down your skin, your bones, your muscles, etc. There was a case of a lady at UC, someplace, I don't know where she was, at a university in California, she was a chemist. She decided she didn't want to be with her husband anymore, and because she was a chemist, she decided she was going to kill him and break him into pieces, chop him into pieces and dissolve him in a vat of hydrofluoric acid, the most active acid. She almost got away with it, but then someone smelled it in the process. So, okay, don't kill people, first of all, okay? Second of all, don't try and dissolve them in acid. You're always going to get caught. But the point being that acid can literally break down your bones. So why do we have any acid in our body? Oh my God. Well, it turns out we need really intense acid to break down a lot of our food, especially our proteins. Proteins get broken down by acid, okay? There are some animals in the animal kingdom that eat bones. The lammergeier, which is a crazy bird, which is a very cool bird, not crazy as an amazing dinosaur, but that literally eats bones. And so it has an even more concentrated stomach acid than we do. Okay, so, but look, lemon juice has an acidity of 2, but why doesn't that, but that's only 1 away. It's actually 100 away from this, because what this is called is a logarithmic scale. So between each, what looks like major tick point, it's actually 10 times as much. Okay, so it's kind of like the Richter scale with earthquakes. So if you have an earthquake with a Richter scale of 5, it's going to do a little bit of damage. If you have an earthquake with a Richter scale of 6, it's going to do a lot of damage, and 7 is intense damage. Even though 6 and 7, those aren't too far apart, but because it's a logarithmic scale, it goes up exponentially each time. Okay, so where are we on the biological scale? So we have things like saliva has a little bit of an acidic. Why is saliva acidic? So it can kill bacteria. Okay, milk is a little bit acidic because it's got that lactic acid in it. Okay, our blood is a little bit basic. Why? We will get to it when we talk about how breathing works, because that's very tightly associated with blood. Okay, but you'll see as pH goes up, acidity goes down. And pH is a measure of acidity. You may see something called pOH, and it's just completely flipped, okay? It's still on a scale of 1 to 14, but if you have a pOH of 0, you have a very, very strong base. We're not going to worry too much about it because only chemists worry about that, and they're not taking this class. Okay, let's move on. Okay. So why does pH matter? If you have an acid, how does it start to eat through things? If you have a bunch of hydrogens just hanging out in this solution of this, what is this? This is going to be some kind of a lipid. And then all of a sudden you have all these hydrogens. Remember, hydrogen wants to go in and break up those oxygen bonds. So if you have a hydrogen come in here and go boom and boom, suddenly you don't have this one nice long molecule. You have two little chunks of molecules. And so that's how pH breaks things down. pH goes in and literally breaks up proteins and other kinds of lipids, especially those proteins that have a specific function called enzymes, and it goes in and it breaks up the structure so it can no longer work. So enzymes have to have a very, very specific structure so that its active site, or basically like the key that goes and unlocks thing, can still fit into the locks, okay? Once you break down that active site with pH, you change the shape a little bit, it doesn't work. So you're going to see in the lab you do that pH is very important in making sure that these molecules can still work. All right, cool. So how do we even get these molecules in contact with each other so chemistry can happen? Because it's not all bad, okay? So pH affecting molecules can be a really good thing when we talk about like oxygen binding to hemoglobin. Well, we want that oxygen to let go of that hemoglobin when it gets to places that need oxygen. So how do we make sure stuff gets to where it needs to go? So the first thing we do is we talk about diffusion. And diffusion is, if I can get this GIF to work, let's see. Here we go. Diffusion is how molecules will very simply just start moving. So these two, we have a warm glass of water and a cold glass of water, and we're going to put some dye in them. Here we go. Oh, it's exciting. And you're going to see that over time, the molecules in the dye just start to spread out. And that is diffusion. Diffusion is the random motion of molecules to take up as much space as possible. Here we go. So yes, there's gravity that's pulling the dye down, but you'll see as it does, it's also spreading out. And what you also notice is that the red one, the hot one, is spreading out faster because the more energy you have, the more diffusion, the faster diffusion happens. So the faster the dye will take over the entire water container, right? But wait, what if the red dye is actually lighter than the blue dye? Well, the lighter a molecule is, the less mass it has, also the quicker it starts to diffuse because those little molecules can move around a lot more. It's kind of like little kids. So little kids, the small, well, let's say like 6-year-olds. The small 6-year-old versus like an ancient 35-year-old in the same room, a bunch of 6-year-olds running around. They have so much energy. They're so small. They can get out of that place and run around so fast, and they diffuse and they take up as much space as possible. Whereas if you're someone who is bigger and older, you might be like, I do not have the energy. I'm just going to sit here. I'll move when I have to. Okay. So things like that are going to affect how quickly you diffuse or move around your space. Okay. Things that do not affect diffusion are pH. No, it doesn't affect it at all. Okay? But things like the amount of energy, the amount of time, and how big something is, those things affect how quickly things diffuse. Now, what if we put like a bridge here and let these two things come together? What would happen? Well, eventually, the blue and the red would eventually mix because, again, they're trying to fill as much space as possible. So how do we know where they're going to go to mix? Well, it depends on what's called the concentration gradient. So the more stuff is in one area, the more it wants to get somewhere else. So let's see. So right now we have a very high concentration gradient here. Do it, do it, do it. Let's say we're like looking at the dye. Is it going to work? Oh, this would be great if I sit here waiting for it to work and it doesn't. Do it, do it. See if I can get it to work this way. Always test your slides before present. There we go. Okay, let's see if I can go back one. All right. So I put in dye here, and you can see it starts spreading out. How does it spread out? Every time a molecule hits a wall, it bounces again. And now look, if you just kind of glance at this, it's pretty well spread out, but they're still moving. It's not that they get to where they're going and they stop. The molecules are always moving, but at equilibrium, there's an equal amount of particles everywhere in your solution, okay? So equilibrium is where you have an equal number of particles going in and out of the same space, okay? So everything is equal, happy, everything's great, okay? If you have some sort of a membrane, like a doorway or something, that allows certain particles to move through it, the same thing happens. Like if there were a membrane here and there was nothing on this side, well, these particles are all still going to move, so everything gets nice and even on both sides. We can think about this the other way and think about the water, okay? So what if there are boundaries in our solutions? Okay, that's what's going on here. Let's boo, boo, boo. What if the whole thing just breaks? That'll be great. Okay, so let's talk about osmosis. So osmosis is where water wants to be equal also, but it's thinking about things the other way. Usually we don't think about water, like if we're making some sort of a dye, like in the case of this dyed solution, we don't care how much water's there, we just care about the dye. But the water cares, okay? So the same thing is going to happen where if the if there's a lot of water in one place, it also wants to move to where there's less water. Okay, because it wants it to be equal concentrations on both sides. So not necessarily equal amount, but equal concentrations. So like this cat could just chill in one or the other, but it wants to have as much of itself in this position as, like, the ratio is the same here. Kind of makes you think about pizzas, okay? So if you have a pizza, if you have a small pizza versus a large pizza, they don't get the same number of pepperonis on them, but they get enough pepperonis that they look pretty even, okay? So obviously this one would have more pepperonis, but it's not it's not filled to the brim with pepperonis. It just looks about the same. Hopefully that worked. So osmosis is the movement of water through membranes until that water is even on both sides, okay? So this is really important when you're thinking about stuff like blood cells. Because one of the reasons why you have to drink water to stay hydrated not just to make sure stuff gets where it's supposed to go, but in the case of it has to do with your red blood cells especially, and just your cells in general. Okay, if your blood cells or your cells are in what's called an isotonic solution, iso means equal, and tonic has to do with the stuff that's present, okay? So like think about a tonic. Tonic water has stuff in it, okay? So an isotonic solution means that the amount of water going into the red blood cell is equal to the amount of water leaving the red blood cell. Now you cannot contain water. Water's going to go wherever it wants. It does what it wants. Thanks, water, you're everywhere, especially in the body. The only thing that is the things that are pretty waterproof in our body are our skin, and even then we leak water, but we do that on purpose when we're sweating or crying or whatever. But our skin is pretty waterproof. Inside the body though, our cells are not waterproof. They're in a bath of water all the time, and that water is moving around, and so as that water is moving around, it's causing changes, okay? So when water is moving in and out of a red blood cell in an isotonic solution, everything's fine. Okay, it means that you have the same concentration of whatever outside as you do inside, which means you have the same concentration of water outside as you do inside. In the case of a hypotonic solution, so hypo means under, that means there is less concentrated stuff, like the salt solution that this blood cell is in is less concentrated than the inside of the blood cell. This is like a fish in fresh water. Okay, so in fresh water, there's let's say no salt, and so you have this fish. A fish in fresh water is peeing constantly because fish are not waterproof, and so water is constantly just flowing into that fish because it wants to get the concentration of water equal inside and outside. Well, the salt can't go anywhere, the proteins can't go anywhere. What's happening? The water just floods in here until it tries to make it even. It's like trying to get a whole bunch of people into a limo at the same time, but there's no more room. What are you doing? Oh my God, someone kicked out a window. What's happening? Well, in the case of water, you're trying to get the amount of water equal on the inside and the outside. So if you think about if this is less concentrated than this, that means there's less water in here because there's more like salts and stuff. Or in the case of the red blood cell, there's more hemoglobin. So that means there's not as much water compared to outside. So the water is going to rush into it to make sure it's got an even number of water. But the problem is the cell will explode after some time. So in the case, if you take a saltwater fish and you put it into fresh water, it will explode. Its body will rupture it doesn't explode like violently, but its body will rupture from the amount of water that's flowing into that fish that it just cannot control. Okay, same thing in cells within the human body. If you are overly hydrated, which can happen, and people have died of it before, water. There was a very famous case where people were doing something for the radio called not weeing for we. So the idea was who could drink the most water and not pee. Okay, so our urination response is very important. It tells us you have too much water, you have too much waste product, get it out of me. Okay, so these people were ignoring their urination response because they wanted to make sure that they won this Wii back when Wiis were all important, the Nintendo Wii. And so this lady, I don't know how much water she drank, but she drank so much that her cells started bursting and she died. Now the opposite happens when you're underhydrated. Okay, so if you're underhydrated, that means that the water in your blood is extra. There's not as much water in your blood as there should be. And so this is like a saltwater fish, okay? So there's this very, very salty solution. Your blood cell, which should be like a little bit of salt, a little bit of water, suddenly the inside of this it has more water than the outside. Compared to the outside, there's a lot more water here. So the water's like, don't worry, I'll dilute it so we're even. And so instead that water leaves the cell and shrinks it and shrivels it down. Okay, now that's why dehydration sucks and you can get dehydration headaches because parts of your body are really shrinking from that lack of water. And so if you have a headache, if you just feel crappy, one of the first things you should do is drink some water because it could just be that you're dehydrated and your body is giving you a response to that. Okay, now imagine if you are a cell and you're nice and like normal and you're doing your thing and suddenly you're so dehydrated, well, stuff can't float around to where it's supposed to be anymore. And so you either rupture, like in the case of this, or you plasmalize, and then all of a sudden you're also dead. And so either way, drink lots of water. All of this is happening through osmosis, by the way. So the water, whenever water is moving, that's osmosis. If it's some other particle that's moving, that's diffusion. And you're really going to explore that a lot in your lab. So what's the difference? Remember that, I have something here. Let's see what it is. Remember that osmosis is the movement of water. But diffusion is the movement of particles. Let's see what this is. Oh, it's boring. It's too boring. It's not working. I don't care. Okay, I'll put the link in the thing. Okay, so what did you learn in this lecture? You learned that I get easily distracted by things. You learned about the difference between osmosis and diffusion. You learned how to build an atom. You learned about the three different kinds of, 3 or 4, depending how you look at it, different kinds of bonds. So you have ionic, covalent, polar covalent, and the hydrogen bonds, okay? And you learned about, I think that's about it. That's a lot. Oh, you learned about the pH scale. Okay, your lab is going to go into these things in more detail, so please go to that next, to lab 2. Thank you. Bye.